Hello everyone and welcome to the channel of Sigma Plus Industrial Solutions. In that video, we're going to talk about the probability and specifically we will discuss the Bayes theorem. So in recent video, we have discussed the basics about the probability and we went through the different type of the probability, such as the classical and the empirical probabilities. And we have also discussed about the union and the intersection of the probability. And today we will give some hints about the conditional probabilities and we will understand the difference between the intersection and the conditional probabilities, as too many people from us they might be a little bit confused when they calculate the probabilities if it is a conditional or an intersection. And we will end up with a good work example which is mainly related to the Bayes theorem calculation, so we can understand when or what could be the situation where I need to implement or to use the Bayes theorem. Okay, so the first thing that start with when we want to understand the formula of the Bayes theorem, from where did it come? So in front of you, you can see a simple Venn diagram where we have two different events, event A and event B, and we have the intersection of the events as highlighted in the blue. So if I say that the subjected to B, so as you can see, the red slash means subjected to the B, or under the condition of the B occurrence, is the intersection between the both events A and B divided by the probability and B. And I can also say the probability of B subjected to A is the intersection of the both events A and B divided by the probability of A, right? So what can I conclude from there? I can conclude the first formula about the intersection, the probability of the intersection between A and B. So I can say that the probability of A and B equal the probability of A subjected to B multiplied with the probability of B, or it's also equal to the probability of B subjected to A multiplied with the probability of A. So the first thing that we can conclude that there is no difference between the both scenarios, right? So based on that, I can conclude that the probability of A subjected to B is equal to the probability of B subjected to A multiplied with the probability of A divided by the probability of B. Okay, now let's look to the second Venn diagram in front of you, where I have different numbers of events. As per the shown, I have A1 and A2 and A3, and I have fourth events, which is the event B, and I want to calculate the probability of B, which as it can be seen from the beginning, that the probability of B will be the summation of the intersection of A1 with B, A2 with B, or A3 and plus A3 with B. And if you have more than other events, that it's the total summation of those intersections, right? So suppose that we have a sample space that has a collection of 3 events, or could be even more than 3 events, and they are all mutually exclusive events. It means that they do not happen or occur at the same time, right? So based on that, as I mentioned, that the probability of B will be the summation of all the intersection of the events with the probability of B. And based on that, if I refer to the first formula I concluded here, where as I'm highlighting, then I can conclude that the probability of B is equal to the probability of B to the subjected to A1 multiplied with the probability of A1 plus the probability of B subjected to the condition of A2 multiplied with the probability of A2 and so on till the whatever is the number of the events that we have. So it's not even ended with the number 3. If you have more than 3, that there will be the total summation of the probabilities, right? So I can conclude another formula here that the probability of B here is the summation of all the probabilities, the B subjected to the condition of AI, where AI is the total number of the events, multiplied with the probability of each event. From I equal 1 to n, where n is the total number of the different events which are mutually exclusive, right? Okay, so we have concluded two rules. Now, if I just look now to the second rule where I have concluded the formula for the PB, so I can utilize this formula and just put it in the first rule, right? So I can conclude now the Bayes theorem that the probability of A subjected to B is equal to the probability of B subjected to A multiplied with probability of A divided by the total summation of the probability of B subjected to each A events multiplied with the P A events, where I would be the numbers of the different events occurring in the sample space, right? Okay, now let's take a work example so we can better understand how the Bayes theorem will work. So in that example, we will calculate all the possible probabilities, and then we will go step by step to understand the Bayes theorem. So our factory is producing three different products: 200 units of product A, 400 of product B, and 300 units of product C. If I have a quality history log reports that's showing that the percentage of failure in the product A is 18%, product B is 25%, and the product C is 10%. So that's the failure rate in each product, right? So I can conclude this, the first probability that I can know is the probability of fail, right? Where I like F is short term to the fail. So the probability of fail subjected to the condition of A means that under the condition that it is the product A is 0.18 or 18%. And again, I know that the probability of fail subjected to the product B will be 25% of the products B, and the probability of fail subjected or under the condition that the product is C is 0.10 or 10%, right? So those are the first information that I can conclude. Now let's go and see all, calculate together all the possible probabilities. If I want to calculate the probability of A, I think it's so easy to calculate because I know already that I have 200 units of product A out of 900 products, where I have 400 from the B and 300 from the C. So based on that, I can conclude that the probability of A will be the 200 divided by the 900, where 900 is the summation of all the products. So I can say that 22.2% is the probability that the product is an A type. And the same will be for the product B, which will be the 400 divided by the 900, and it will be equal to the 44.4%. While for the product C, the probability would be 33.3%. Okay, so if I'm speaking about the probability that the product pass, so we know already the fail rate. So it's very easy to calculate the probability of the pass in each type. So if it's 18% for the 200, so that will be 82% for the product A. 25% fail rate for the 400, so that means that the pass rate would be 75%. And I have 10% fail rate in the product C, so that means that I have a 90% rate for the product C. So if I want to know the probability of the past product, regardless the type of the product, so that will be simply the 82% of product A plus the 75% of product B plus the 90% of the product C divided by the 900, which will be equal to 81.5%. And then I can calculate easily also the probability of fail, either that I calculated 100 minus the 81.5, which will be 18.5%, or you want to do it in the same way that we have calculated the probability of pass. It will be also equal to the 18.5%. Okay, now when I'm looking to the intersection probability between pass and the product A, that means that the probability of pass intersection with the probability of A. Okay, so if I look to the Venn diagram, so I will see that my intersections would be the 0.82 or the 82% of product A divided by the 900 units, right? Which is the total number of the units. So that will be 18.2%, right? So 0.82 multiplied with the 200 divided by the 900, which is 164 divided by 900, which will be equal to the 18.2%. Again, the same point for the probability of pass intersections with B, which will be the 75% of the product B divided by the 900, which is the 33.3%. And the same thing for the product C intersection with the pass, that will be 30%. And again, the same thing that we have done for the probability of fail intersected with A, and probability of fail intersected with B, which is 11.1%. Probability of fail intersected with C, which is 3.3%. So it sounds easy, right? We don't see any complications, okay? But it's very important that we go through all those steps, because later on when we will go to the Bayes theorem, some of those probability we will need it, so we can compare the results before and after implementing the Bayes theorem, okay? So let's dig more now in the subjective conditions or the conditional probability, okay? So in the first step of the example, we have highlighted the probability of fail subjected to A, and now we want to calculate the probability of A subjected to fail. So please understand that there is no difference in the formula, but that doesn't mean that the value of the both formula and the both calculations will be the same, right? The values will be different, but the way that we are calculating the formula itself, there is no difference. Okay, so here when I'm speaking the probability of A subjected to fail, or under the condition that the product is a fail unit. Okay, so the fail unit is as I highlighted in red here. So that will be my sample space, right? And the product, so my probability of A under the condition that the product is a fail will be the 18% of the product A divided by the sample space of fail, which will be the 18% of product A plus the 25% of product B plus the 10% of product C, right? And let's see the result, which will be 21.6%. Okay, so there is a 21.6% probability that if the product is failed in the test, that it will be an A type. Okay, so I can do the same for the other type of the products, for the product B, which was found to be 60.2%, the product C, which was found 18%. And those are the probability of each product type under the condition that the product is failed in the test, right? We can do the same for the product fail. Okay, here I just wanted to highlight it. That was the basic information that we have known at the beginning of the problem, where the probability of fail subjected to A was 18%, right? So probability of A subjected to the probability of fail under the condition that it is an A product, okay, so what does it mean? So the fail probability, which is 18%, okay, out of the 200 units under the sample space of the A, right? So that's what we mentioned about the because the sample space of the product A is 200, so we know that the probability of fail subjected to A is 0.18. Okay, and the same for the product probability of fail for the conditions of B occurrence is 25%, and the probability of fail subjected to the C type is 0.10 or 10%, and those are the basic information. So just keep in mind that yes, the formula could be the same to calculate the is the same to calculate the P subjected to fail or P fail subjected to A, but remember that the values won't be all the time the same, right? Okay. We have one same for the probability that the product is an A type under the condition that it is a pass. So if it is a pass, so that means that my sample space now will be the 82% of the product A plus the 75% of the product B plus the 90% of product C. So the probability of A subjected to pass will be the 82% of the product A divided by the 900 multiplied with those probabilities, or sorry, the probabilities multiplied with each quantities of those product type. So we can see that the probability of A subjected to pass will be 22% or 22.3%. The probability of B subjected to pass condition is a 40.8%. Probability of C subjected to the pass condition is 36.7%. And again, we have the probability of pass subjected to A is 82%, right? As it's highlighted here. And the probability of pass subjected to B would be 0.75 or 75%. Probability of pass subjected to C is 90%, right? Now, we have concluded all the results. So as you can see, what did I do here is that I had listed all the answers here, because now what we are going to do, that we are going to calculate the BIOS. We are going to use the calculation of the formula of the BIOS theorem to calculate the probability of B subjected to pass conditions, right? And we have it here, the probability of B subjected to a pass conditions. We found it 0.408 or 40.8%. Okay, so let me highlight for you a simple point here so we can understand, okay, so what will be the need to utilize the BIOS theorem, since that we could calculate it in a simple way. See, uh, in the first case, for the first scenario, we know the number of units, right? The number of units for each product type. So we know that we had about 200, the 200 units for B, and we had, if I remember, the 400 units for the B, and we had 300 units for the C, right? But suppose in certain conditions that you don't have those numbers, okay, and you still need to find the probability of the B subjected to the condition that the product is a pass. Now we can calculate those probabilities by utilizing the BIOS theorem. So based on the BIOS theorem, the P probability of the probability of B subjected to the pass will be equal to the probability of pass subjected to B multiplied with the probability of B divided by the summation of all the events, which is the probability of pass subjected to A multiplied with the probability of A plus the probability of pass subjected to B multiplied with the probability of B plus the probability of pass subjected to C multiplied with the probability of C. Okay, so based on that, we have some informations that could be, or most of those data could be easily found. So if I just, okay, the probability of pass subjected to B is 75%, right? Multiplied with the probability of B, which also was easily found, and it was 44.4%, divided by the probability of pass subjected to A, which is 0.82, right? And multiplied with the probability of A, where the probability of A we calculated at the beginning, and it was the point 222 or 22 percent, 22.2% plus the probability of the pass subjected to B. So the probability of pass subjected to B is 0.75, right? As I'm pointing, and multiplied multiplied with the probability of B, which is the 44.4 the 44.4%, plus the probability of pass subjected to C, okay, which is the 90%, so it's 0.9 multiplied with the probability of C, which is the 0.333. So that will be equal to 0.333 divided by the sum of 0.182 plus 0.333 plus 0.229, and that will be equal to 40.8%. So the probability of that the product is a B type under the condition that it is passed from the test will be 40.8%. So as you can see, the difference here that we don't know the numbers, right, of the units. So we don't know what are the units numbers for the different products. So through the Bayes theorem, we could calculate those probabilities. Now you can continue do those exercises if you want to calculate the probability of A subjected to the condition that it is pass, or the probability of C subjected under the condition that it is a pass product, and utilize the Bayes theorem. Okay, so at the end of that video, I hope that I could explain to you the Bayes theorem. I thank you for your good listening and watching, and see you for the next time. Thank you.